Well, good afternoon, folks. I want to thank you all for joining us this afternoon for the sixth of seventh installment on the Summer STEM series, where we're talking about different topics having to do with STEM and diversity and a lot of other issues that typically we don't talk about in science. And today, it's a pretty big deal today because we're going to be talking about nanotechnology and nanoscience. And in today's presentation, the panel is not only going to introduce you to the world of nanoscience and technology and the way that it overlaps with other STEM disciplines, but they're also going to be talking to you about their personal journeys and how they got to be where they're currently at. And so, the way they're going to be able to do that is after this presentation that's going to introduce you to Nano, we're going to be having a panel discussion, again, on applications of nanotechnology and also potential workforce opportunities. So we have three dynamic guests that will be joining us today to be doing that. You're joined today by Veronica Bunn from NIWC Pacific, with Dr. Jared Ashcroft from Pasadena City College, and Dr. Oscar Vasquez Mena from UC San Diego. And so it's a real pleasure to have you all here, and we are looking forward to the conversation. Before we get started, I did also want to ask you all out there in the audience, if you could please, just to kind of give our panelists and guests an idea of who's out there, if you could, in the chat, tell us what school or what grade level you're at, whether you're an undergraduate and such, community college, or if you work for a company or an industry, if you can let us know who that might be, just so we can get a sense of who's out there. And then also what I'd like for you to do, if you could, is to start thinking of questions that you might want to ask panelists, so that towards the latter part of the presentation, or the session, better said, we can make sure that we ask these questions to our panelists and pick their brains about their wisdom on this wonderful topic. So today I'm also joined by my co-conspirator here, Dr. Olivia Molinar Ingles, who is going to be co-moderating with us. And Olivia is a researcher from UC San Diego as well. And so thank you, Olivia, for helping us out. And thank you, Laura, also, who is taking care of all the just pretty much everything having to do with these sessions. So just want to take a moment and acknowledge all the work that you do on that end. So without further ado, I want to go ahead and ask my co-conspirator here, Olivia, if she would mind introducing our guest.
Hi, thank you, Beto. And again, always, I appreciate all the time and effort you take into incorporating me into these awesome initiatives. Well, I'd like to introduce everybody to our panelists. And as you all, I'm also very new to Nano. I'm not a engineer. I'm actually a biological sciences scientist. So like you guys, I'm going to have a ton of questions. So please write them down, and I will write them down myself, because I'm really intrigued on what is nanoscience, as well as how we can apply it. So I'm going to begin with Veronica Bunn. She is a Texas native. Woo woo! I'm also from Texas, so glad to have you here. She got her bachelor's in science in computer engineering technology with a minor in security from the New Mexico State University, where she was the president of the Society of Hispanic Engineers and also a leader in supporting STEM projects on campus for all youth in the area. She is currently working on her Master's of Science in Cybersecurity Information with a minor in Data Science from UC Berkeley. She's also the Vice President for the Ministry of St. Vincent Paul Community Outreach Program, providing essential food and shelter to low-income families. So thank you so much for not just being an awesome engineer, but also for helping us and for helping everybody, achieve a lot of more positive and better things, such as, the outreach that you do. So thank you so much for being here. The next panelist we have is Dr. Jared Ashcroft, who graduated with a Bachelor's of Science in Chemistry from Long Beach State. And he is developing carbon. He attended Rice University, where he worked with Dr. Lon J. Wilson, developing carbon-based nanobio immunoconjugates for use in medical applications. So after he earned his doctorate in chemistry from Rice, he moved to Berkeley, California, to work with Dr. Carolyn Larabel's National Center for X-ray Tomography at the Lawrence Berkeley National Lab. And now he is currently a professor at Pasadena City College, where he runs an amazing program for undergraduate research attempt to infuse active learning, as well as providing accessible microscopes. So if you have any questions on outreach, as well as anything about Pasadena City College, you have an awesome professor here. And now he's currently actively involved in bringing nanotechnology, technician education programs to community college campuses. Thank you so much for being here, Dr. Ashcroft. And lastly, but not least, is Dr. Oscar Vasquez Mena, which I've heard amazing things about. He received his bachelor's in science and physics and engineering from Monterrey Institute of Technology in 2000 in Mexico. And then he went abroad to get his master's of science degree from Chalmers University of Technology in Sweden. He got his PhD from the Swiss Federal Institute of Technology at, I'm gonna correct me if I'm wrong, Lucerne, EPFL in Switzerland. He did his postdoctoral research at the University of California, Berkeley, in the Department of Physics. And now he's a assistant professor at UC San Diego. Thanks so much for being here. And also, one thing I'd like to point out is that at UC Berkeley, he founded the Indigenous Pipeline Program, aiming to increase the access to UC Berkeley to children from Indigenous backgrounds. So thank you very much, Dr. Vasquez Mena. With that,
so thank you.
Go ahead, Beto.
Oh, thank you, Olivia. So thank you all very much for joining us this afternoon. I also wanted to take a moment to give a shout out to some of our co-branding organizations, right? So I wanted to give a shout out to RAIN, which is a remotely accessible instrumentation for nanotechnology, always a mouthful, and also the NNCI, which is the National Nanotechnology Coordination. Man, I always butcher that. Okay, NNCI, infrastructure, I'm sorry. There you go. And so I just wanted to give a shout out to them. So these are major bodies out there in everything nanotechnology and nanoscience, and also locally to the San Diego Nanotechnology Infrastructure for their support and for the great work that they're doing to get information out there about nanoscience and nanotechnology to the general public, so that you become aware of the different opportunities available within such spaces. So you know, we got to hear a lot of the great stuff that we usually would read on a bio, right? Sounds really good. These are amazing opportunities that these individuals have participated in. But I want to ask our panelists, you know, to kind of dive a little deeper, right? Because I know as an undergrad, sometimes I would read bios and you know, it's somewhat intimidating to see some of these folks and interact with some of these folks. But I want to ask you if you wouldn't mind sharing something a little bit more of a personal layer of yourself with us, and tell us maybe within 3 to 5 minutes how it is that your journey got you to where you're at. So all those wonderful accolades that we get to read about you within your bio. So maybe Oscar, if you wouldn't mind getting us started, you know, a little bit about your journey.
Yeah, thanks, Beto. So I would say that my journey was a little bit different from what I suppose people would tell me that was the normal route. I always hear that, you know, you had a goal and you have to go for that. And, you know, if you have a dream, you can always get it, right? I can tell you, when I was doing my undergrad, I never thought about nanotechnology. That wasn't at all in my mind. I got into nanotechnology basically because I wanted to go to Canada to do electrical engineering. And I wasn't accepted in the school that I wanted to go. So I got this opportunity in Chalmers that for me was like the second. I mean, I was like, oh, well, I wanted to go to Canada, but I will take this chance. And I went to Chalmers and they were starting one of the first programs in nanotechnology, in nano engineering. And I just love it, right? It was like an amazing thing, you know, but it was back in 2000 when nanotechnology was like starting to become a big, big thing. So that for me, that was very important because I realized that, you know, sometimes the second opportunities are even better than what you were aiming for. And that's something that I want to share with kind of a lot of the underrepresented minorities. You know, it's going to be very tough to get it sometimes into the school that you want to go. You know, we have goals. But, you know, sometimes life has on the side has excellent opportunities, right? It's like going on a trip and just planning to do whatever you want to, right? That could be a very kind of boring journey, right? Of journey of preparing holidays. I think the most exciting thing in life is what happens when you don't plan it, right? Things that happen on the side that you didn't think that it was going to happen. And sometimes in those spots, life can give you very nice opportunities. Also in Berkeley, I mean, my plan was supposed to go to chemistry in Berkeley, and then I met there a physics professor that I met like 5 years ago. He told me what he was doing, and that's how I got into graphene, right? So many of the best things that happened in my life, I didn't plan them. It was more like, oh, I was there and I was trying to do something, and then I found these second opportunities, and these second opportunities were really way better than what I was planning ahead. So what I want to say is just like, always try to move forward. And if things don't go the way you want, keep going and just look for those opportunities, because in those side opportunities, you will find a lot of excitement. Thank you.
Excellent. Thank you for sharing that, Oscar. Always great to hear a little bit more of the back end of things, right? And Jared, I'm going to ask you now if you can share a little bit about your journey.
Maybe a little bit about my journey. In high school, I went to Avila High School in Chino Hills, and I always wanted to teach. Always wanted to teach science, and I got to Long Beach State my first year, and I realized that if you don't go to class and if you work 50 hours a week, and you have a girlfriend that breaks up with you, and basically all these life experiences, you end up with a 2.1 GPA and almost kicked out of Long Beach State, which would actually be an amazing feat, seeing that it's a Cal State and it's not the most competitive place to be. But after my first year, it was a struggle, and just getting to where you're at. I think one of the big lessons that I've learned is put yourself in a position to succeed. Like, you can't work 50 or 60 hours a week. You have to really be engaged and actively pursue what you want to do and take advantage of opportunities that are given to you. What really changed for me is I started to take my science courses, and I'm a chemistry professor, and I'll be honest, I was marine biology at first because I love marine biology. I wanted to be on the ocean all the time, and then I realized you can't do anything with marine biology a whole lot with it. And so I really liked my chemistry teachers, and I was getting A's in it. So it really wasn't the chemistry. It was just like, I really loved the teachers, and I did well in it. So I changed to chemistry, which was awesome. Because once you get to the upper division courses, it gets a lot more exciting. And I always wanted to teach. And then I realized, like, oh, they're going to pay me to go get a PhD, right? Like, that's the nice thing about science and chemistry and STEM is that, like, if you want to go get a PhD, they're going to pay your stipend. They're going to pay you a stipend. They're going to pay your room and not room and board, but they're going to pay your tuition and all of that stuff. So I applied to 4 different schools. I applied to Rice University only because they were the first school that actually sent me a free application form. I didn't even know where they were at. They're in Houston, Texas, by the way. I learned that after I got accepted to it. And the cool thing about graduate school, they actually bring you to the campuses to sort of talk to the professors, and they, in a way, recruit you. They pay for the trip for science majors, and I really love that campus. And that's another thing I would really suggest, like, go and talk to people whenever you're applying for grad school or undergraduate school where you're going to transfer. Get to know the campus before you go so you make a more informed decision. I got my PhD at Rice, and I ended up going to the Lawrence Berkeley labs, and probably the thing I learned, that was my postdoc. I was thinking it was going to be 2 years, and I was told beforehand that the professor I was going to be working with is a kind of piranha-like. She likes to just, eat you and spit you out, basically use you and get whatever she can from you. And about 8 months into it, I'm thinking it'd be 2 years. And I sat down with her, and I published 2 papers with her within the first 8 months, and nobody publishes in that group at all. So I thought, oh, I'm doing pretty good. And she sat me down and said, "You have any funding coming in?" And I'm like, "Nope." And she said, "Well, you're done in 4 months." So from that experience, the one thing that I learned is you have to make yourself needed by a group. You have to come up with your own ideas. Like, my mistake in my postdoc was I was just doing ideas that they wanted me to do, and I never presented my own research. So think of your own ideas, think of your own things that you can do. Otherwise, what happens, what happened to me is you kind of, all right, you're not going to be able to do anything for me anymore, and you get kicked out. It ended up being the best thing ever because I was able to get a job at Cal State Fullerton, teach chemistry for 4 years. Then I got my job at Pasadena City College, and now I do run the Micro Nanotechnology Education Center, which is a NSF ATE grant for the National Science Foundation out of Pasadena City College, which just started here in July 1st, actually.
Awesome, and congratulations once again for that. And thank you for sharing that very informative horror story there. You want to scare some of our students here from applying for graduate programs there. But absolutely, I couldn't agree more. I think it's so important that we value not only are we good enough for the school, but is the school good enough for us, right? Are they going to meet the different needs and expectations that we might have as individuals? But that's also going to require for us to be able to place a value on what we have to offer to our respective team. And I hope our next panelist, as she introduces herself, she could tell you a little bit more about how folks are able to do that. Veronica.
Thank you. I guess pivoting on what both Oscar and Jared have said, I do have also one of those second chances, failure results of where I'm at now. I was divorced with 3 children, toddlers, that when I started my engineering degree. I finished my engineering degree in less than 3 years, being a full-time mom and working full-time from NMSU. So it was one of those very quick, that I had to. It was something that I needed to do to provide for my children. So what that happened is it kind of gave me a sense of, I can do this. There's not, as long as you set your mind and you have that willpower and the drive to go, there's nothing you can't do. So my career started there. I was a jet mechanic when I was in the military way back. So I had that, that engineering mind, that mechanical mind. So it really pivoted me to where I wanted to end up. So again, the instructor, the reason I started the DOD and I started right after college is my professor said, hey, this sounds really good at what you're doing. Why don't you go in and apply? So the DOD was recruiting local, newly graduates. So I just happened to be blessed to get one of those interviews, and it just happened out of Starbucks. It was very quick. It was just, one of those, again, like Oscar says, those paths that life sends you, that you just have to take them because you never know where you're going to end up. And I started as a contractor, just so that they would test the waters to figure out if you're the right person with the right skills and what you needed. Working very, very hard. I was very fortunate to become a government civilian within 6 months. So I've been, I've had this job for going on 16 years starting in November. So I've been very blessed, working hard, trying to get everything done, and so I have 3 children, 21, or actually 22, 21, and 18. And my oldest is getting ready to finish her college degree. So as I show by example, I said, okay, I got my undergraduate. I need the next hurdle. And in order to inspire her, I decided to go back and go to school at my 50+ years of age. You're never too old to learn, and you're never too old to start your mission. So again, somebody asked me, well, where are you going to, apply to? And I'm like, you know what? I'm going to Berkeley. Just like Jared said, didn't know, just figured I might as well. If I get shot down, I'm not, I honestly thought I would never get accepted. I was very blessed to get accepted. I love the program. And I've got 1 more semester to complete my master's. And then I just decided that, I love it so much that there's so much to know that I added another master's to it. So it's kind of a double major. My daughter's like, Mom, I already got the, you're showing me the example, but I just love to learn. And it's just so much to do that, if you're willing to show that you have the drive at whatever age and whatever stage, nothing is, nothing's the limit. You can do whatever. I'm actually already thinking of going to do my doctorate, decided where that's going to happen, but it's been a really awesome path for me, and I love what I do. That's one of the things I love to tell students, or, whatever age you're at, if you love and you have the passion and you love what you do, there's nothing that's going to stop you from achieving that goal. You might have some bumps and bruises along the way, just get up and scuff those knees and keep on going, because that's what makes you in the long run the stronger, the better person, is if you're able to bypass those obstacles, whatever life brings you. That was what makes you who you are.
Wow, pretty amazing, amazing stories here. Thank you for sharing that, Veronica. It's interesting. Many of you might not know a lot of nanoscientists, right? But here you are. You have 3 wonderful examples of folks that have to interact on the nano level. Scientists, by all means, and yet you're hearing three very down-to-earth messages, messages that aren't convoluted with just complicated language and technical this and technical that. So it really relays and conveys the message that nanoscience and nanotechnology really is for anyone that wants to receive it. Olivia, would you lead us to the next place, please?
Sure. I just wanted to make a quick comment. Nothing to do with nanomaterials, but I hear Rice, Houston. I hear NMSU, and I hear Texas, and then I hear Monterrey. All those are really similar and really close to Texas, and I'm from Texas. So I think, just making that connection, all of us from Texas are doing great things. I'm just kidding. California is also. But anyway, I'd like to lead into the, to the question, and maybe Dr. Ashcroft, if you would go ahead and enlighten us with what, nanotechnology is. I'm thinking, can I use it to, see my cells? Can I use it to apply to biology? And that's kind of the things that I'm thinking about right now is nanotechnology. But you can go ahead and let us know what nanotechnology is.
Jared, you're on mute, so we'd love to hear what you're saying.
That would be awesome. I hate when I do that. No, thanks. So hopefully I can do a good representation of what nanotechnology is and kind of show you how cross-disciplinary and multidisciplinary it is. Again, we like to say it's the science of small. So I do run the Micro Nanotechnology Education Center at Pasadena City College. That's a national center that tries to improve technician education in nanotechnology for students across the country. You can kind of see here on the bottom left, that's actually a SEM image. It's about 60,000 times magnification of a blue morpho butterfly wing. If you look at these little structures, that's only about 400 or 500 nanometers apart. And that's really what causes that blue color in the blue morpho butterfly wing. There it is. So here's a typical day, somewhere in the world. And if you look at all the nano-based products that are out there, your mobile phones, bike frames, that's materials, mobile phones, all the semiconductors, all the electronics in it, biomaterials, the artificial lenses or for artificial hits, glass or coatings for optics, UV. Nanotechnology is widespread. There's trillions of nano devices that are out in the world, and we need people to get educated in nanotechnology. So all the jobs that are going to become available, and a lot of people are retiring right now, we need students, and we need people who can take the place of those employees that are leaving the workforce. It's a great need right now. Just here's some applications: medicine, health, IT, energy, material science, food, water, environment, instruments. You could choose so many different avenues of employment and research if you're looking into going to nanotechnology. Just a really quick industry, the CAGR, that's basically how much nanotechnology products are going to be worth in 2024. You're talking about $35 billion. It's probably actually higher than that. We're having about a 9.6 increase in the industry needs and the industry products out there. And that's just for micro electromechanical systems, which are MEMS. Basically, think of any little gear that's inside a computer or any kind of really small sensor out there. Those are what MEMS are. That's really how a lot of the electronics are ran in our society. There's a million jobs, we can give or take in nanotechnology available out there. And again, there's going to be a lot of them available. I talk to industry quite a bit. There's going to be a lot of jobs available over the next 5-10 years. And again, it's about $1 trillion industry right now. So part of what our center is and what we're trying to do at PCC and even in the community is how do you bridge converging technologies and micro nanotechnology industries and research universities. The thing I love about micro nano is it's not really a specific subject. It's sort of like chemistry, how chemistry is sort of that fundamental science that bridges everything together. That's really what nano is to engineering and science. You can do manufacturing, you can do nanobiotechnology. There's some really cool COVID-19 vaccines that are being developed that are actually based on nanotechnology. Photonics, which is really how light interacts with really small objects. Physics, chemistry, healthcare, it's all over the place. So I wanted to kind of do this video for fun because this is not nano, but maybe for fun you can think, what video game is this?
I have it.
Monkey's outside right, so be careful.
Who wants Nano?
Yeah, so I'll stop it there because it's Nano Boost in Overwatch, which, you know, I don't know how they get Nano and why they have Nano Boost in there, but that's how kind of widespread it's becoming. Is it's in video games. Like, you play video games. I play video games. I love video games. I won't lie. And you see in these different games nano concepts. Over here on the bottom left, this is a Nano Hummer. I don't understand how a Nano Hummer really exists, because Hummers are really big and Nano are really small. This is another car that they've made, which is the Nano. This is not really Nano. You know, this is kind of fun, and it really doesn't have what our applications are. So what exactly is Nano? And I have a couple of videos I'm going to show. This one's a really interesting one from MIT on nano soldiers.
The nano-enhanced super soldier possesses abilities and tools unsurpassed by any military technology in the world. Nano-reactive muscle propulsion increases jump height by up to 6 times. Anticipatory projectile deceleration predicts and protects against a variety of gunfire. Spasmodic restabilizers snap fractured bones back into place and form an instant cast around the injury. The situational assessment visor goes beyond night and heat vision to identify allies, enemies, and mission objectives. Finally, adaptive stealth makes the soldier invisible to all electronic forms of detection and even the human eye.
So those are kind of a lot of materials science, you know, like using nanomaterials in ways that, and it is true, like you can have a nano suit on that can detect whether your bone's breaking and be able to kind of change its form to sort of make a splint. Where the idea, like that's not in the video, but where they would actually do CPR, the suit would recognize that your heart rate isn't where it's supposed to be and start doing CPR on you. So, you know, this materials and being able to create things at the atomic level, and using that in order to bring products and these type of applications is really prevalent in nanotechnology. I'm not going to show all the videos that I have. Another really, really large, you know, huge area of nanotechnology is in biotechnology, using drug delivery to fight cancer. And I'll kind of show you this one just to show you how these nano-based drugs work and delivery.
Cancer cells isolated from human tumours can be used to help the development of novel cancer therapies. For most drugs to be therapeutically active, they must go inside the cell. Nanoparticles carrying drug payloads can be used to facilitate the drug delivery. Nanoparticles can be targeted to receptors that are overexpressed on the surface of cancer cells. They then enter the cells via a process called endocytosis. Antibody fragments engineered on the nanoparticle bind to the receptors, initiating the internalization process. Inside the cell, clathrin proteins form a cage around the developing endocytic vesicle, which is then cleaved from the cell membrane. The newly formed vesicle carrying the nanoparticle travels further inside the cell, where it is captured and fuses with an early endosome. Inside the acidic endosomal compartment, the nanoparticle degrades, releasing the therapeutic cargo, which induces a controlled death of the cancer cell. Nanoparticle-based drug delivery provides a novel and targeted approach for the future of cancer therapy.
So that was actually what my PhD work was on at Rice University, was taking and making immunoconjugates of nanoparticles. I was the first one that actually attached an antibody to a nanoparticle, which is a fullerene, and that was one of our first publications for me in that group. Another, kind of interesting topic is nanobiology. Is how does the nano create nature? So you think of blue morpho butterfly wings. The blue morpho butterfly wing, this really beautiful blue color right there, those are actually nanostructures. It's not pigments. How light hits those nanostructures and how light interacts with it causes this blue color. And we can actually change that color by putting different solvents on there in order to get different light diffraction. And you can see if it's in ethanol, it turns green, or if it's in sugar water, it can turn black. So again, nano is all over the place. In nature, it's in medicine, it's in materials, which you saw with the nano soldier. Here's a really close up of the butterfly wing. And I just wanted to stay here. Like, there's a program out there called the Remotely Accessible Instruments and Nanotechnology RAIN Network for any student who wants to have access to a scanning electron microscope, atomic force microscope, transmission electron microscope. We offer them free of charge. And you could just sign up and make a time that you want to come and look at these different structures. So just type it into the search engine or go to nanoforme.org. I'll type it in the chat once I get done with my presentation and see what kind of images that you can get. Here's a really cool, I'm not going to show the video, but you can actually, based on nano, create kind of Spider-Man like walking up a glass surface, and it's really based on geckos' feet. Geckos have these really tiny hairs at the end of their feet called ciliae, and they're based on van der Waals forces, and they're nano-sized, and that's really why geckos can walk on glass. It's because of the interaction of the glass with those ciliae. And at Stanford, they actually made a similar one that makes it so they could walk up the glass at Stanford University. Yeah, this is the nanoparticle bioconjugate that I made. We just took an antibody, attached it to the fullerenes. Here's the different things that you can change in nano. We can change the surface. We could attach different types of things on the surface. We could attach drugs. We could attach antibodies. Drugs would be for the actual use of medicine. The antibodies could be like to get specific cancer cells. We could change the shape of nanos. We can change the size of nanos, and you could change the material. We could use carbon-based material, silver nanoparticles, gold nanoparticles, titanium-based nanoparticles. You could even make nanoparticles out of biomaterials. They call them micelles. So there's a lot of different things that we can change in nanochemistry. Here's just kind of the difference. If you have gold, like gold at the nano level is no longer going to be gold. It's actually going to be purple or red based on the size, and we can change those colors based on the size of the nanoparticles. And we can actually create different sizes and shapes based on just doing chemistry and different chemistry reactions to them. We can add external molecules. This is actually a C3 compound. It was developed about 15 years ago by a guy named Steve Wilson, and it was actually one of the best drugs out there for Alzheimer's disease. Alzheimer's disease is a brain degenerative disease, and it's created by free radicals that attack the brain and kill it. So this C3 molecule is a radical scavenger. It goes and eats those radicals, which are just free electrons. It's like an electron that's all by itself. And it was interesting, they put that compound in rats. They fed rats this molecule for an extended time, and those rats lived about a year longer than rats that didn't have it. So it looked like it actually extended your life, because free radicals are actually something that actually ages you as well. We put Taxol on a fullerene, which is a cancer-fighting drug. So you can attach a lot of different external molecules. Attach antibodies, get the specific cell delivery. And here you can see the gadolinium-based nanoparticles. They just glow a lot better for contrast agents. If you're going to try and detect cancer earlier, which is really the best fighting of cancer, to get it in remission at an earlier stage, these gadolinium nano-based drugs have much better contrast than the drugs that we use today. So here's an invitation. We have a micro nanotechnology student ambassadors program through our new national center. So if you're interested in getting involved with nanotechnology at a kind of a technician level, or even for research, we do have undergraduate research projects that we're doing remotely. Send me an email, contact me. I'll put it in the chat, and I'd love to have you come to our meetings. I kind of like to end with this slide of just the students. This is really the goal, is let's give students opportunities to present, to do research, to get involved in a community. And that's kind of what the goal of our Micro Nanotechnology Student Ambassadors Program is. So I'm going to stop sharing and pass it off to Oscar.
Okay, can you hear me? Good. Okay, so I want to talk about nanotechnology, basically just focusing in one important aspect of society, which is information technology. So, I mean, definitely nanotechnology, as you already mentioned, I mean, there's so many things that can be done. And I'm just trying to kind of organize in two kind of routes. Something that nanotechnology can do is definitely improve the capabilities of the devices that we have right now. Basically, one of the main driving forces in any like information technologies, we want to have devices that store more information, right? The more stuff we can put in the mobile phones, the happier we are, right? Right now with all this Zoom chatting, we're just recording a lot amount of information in video, so we need more storage, right? We want faster operations, right? We want to deliver information faster. We want to make computational operations faster. Everything has to go faster, right? And we also want lower power consumption, right? The less energy we consume, the better. So like nanotechnology, we can essentially make transistors smaller, right? And if they are smaller, we can put more of them in our cell phone so we can have more memory. We can have more transistors doing operations in parallel so we can run simulations and operations faster, right? And of course, for example, if we have a transistor that works with only one electron instead of having a transistor that works with 50 electrons, it's always cheaper in terms of energy. We require less energy to charge a transistor that only works with one electron. So with nanotechnology, we can also reduce the power consumption. This is what I call improved capability, right? Extremely relevant. But I would say to some extent, scientifically, not so exciting because it's just stuff that we kind of know that is going to happen, right? The other route of nanotechnology is unprecedented capabilities. The stuff that we cannot do right now with macro stuff that we can do with nano. And that, I'm just mentioning a few examples, but there's stuff there that we don't even know that may be done, right? But nanotechnology, by doing experiments and discovering and pushing the limits, we're finding new physics, new ways of doing things. So an easy one is, for example, now we can change the color of a particle just by changing the size, right? If I take a piece of gold, it doesn't matter the size of the piece of gold that I have, I know it's gonna look kind of yellow, right? When we go into the nano stuff, then we see that by changing the size of a particle by 1 nanometer, the color changes, right? Another that is very exciting that I'm gonna tell you is finding electrons without mass. We all know that the mass of an electron is kind of a fundamental constant in physics. The mass of an electron is like very fundamental. And now we find electrons in graphene that behave as phantoms. They don't have mass. Quantum computing, right? That's also fundamental. That's also a capability that nanotechnology is bringing, that we can have now like bits of information that talk to each other and make calculations more efficient, right? This is what I call unprecedented capabilities. So just for the sake of time, I'll just kind of go ahead and talk a little bit of this. For example, semiconducting quantum dots, right? So the nice thing about these particles is that you change the size and you change the color, right? Of course, that doesn't happen with all type of particles, but that normally happens when you have semiconducting particles, typically less than 10 nanometers, right? If I take a piece of cadmium telluride, you see a certain aspect, a certain color. Cadmium telluride is going to absorb a certain kind of light and it's going to reflect a certain kind of light. And if I chop this bulk crystal in many, many pieces, the color is going to be the same, right? If I start making them smaller than 10 nanometers, between 3 to 10 nanometers, I can see that the color that is being emitted or absorbed by small cadmium telluride particles, it's going to change, right? And that's that is has a lot of potential for TVs, right? Because now we can use the same material with the same processing to have pixels of different colors, right? Let me see. Yes. Why is it? Oh, I found correct. I start my video. Sorry. Sorry about it. Okay. So of course, one question is like, I like this thing. Why is it that different particles with different sizes have different colors? Well, the answer is maybe a little bit complicated, but I can tell you it's the same reason why strings of different length have different frequencies, right? If you remember your mechanics or, the acoustics or, mechanical classes, when you have a string and you put some tension, you have some natural frequencies, right? If you make this chord a little bit smaller and smaller, you change the frequencies. Right? It's the same physics in these quantum dots. So if you shorten the string, then you have higher frequencies or higher energies. The same with these quantum dots. You decrease the size of these particles and you change the energy levels. And now you have basically higher energy levels. And that's what kind of brings the light emission or light absorption to higher energies. And basically changing the energy, you change the frequency and you change the color. And what is really cool is basically that the equations that describe this string, the motion of the string, are very similar to the equations that describe how the electrons behave in these nanoparticles. Different scales, different materials, but yet the math is very, very similar. And that's amazing when you connect these dots, and this kind of the beauty of nanotechnology, that you still have mathematical models that reflect some of the real life in reality, but at different scales. The other one that I wanted to talk about is graphene. And let me see if I'm doing with the time. So graphene is another beautiful material. It's just a monatomic layer of carbon atoms that form a hexagonal lattice, right? Looks beautiful. It's simple but beautiful, right? And it's only one atom thick. Before I go and I tell you about the properties, just remember that the way you put things together is very important. And if you're going to do nanotechnology, you have to think not about just what you put inside, but how you put it inside. This is graphite. This is diamond. Completely different materials. One is opaque, very, very soft, and conductive. The other one is the opposite, transparent, the hardest material, and a terrible conductor. And yet they are made of exactly the same atoms, carbon atoms, the same carbon atoms. The only difference is how you put them together. In the case of diamond, you have a three-dimensional lattice. In the case of graphite, you have them like kind of two-dimensional layer by layer. And just this different arrangement gives you completely different properties, right? And that's what happens at the nanoscale as well. When you start playing, you can have the same type of atoms, but if you put them in different configurations, you get completely different behaviors. So graphene has kind of like three kind of records: the thinnest material, the strongest material, and the fastest material. The thinnest, simple, is just only one atom thick. And carbon is already a small atom. So it's going to be a difficult task to break that record. You can go for making a two-dimensional layer of hydrogen or helium, and that would definitely be thinner than this, but that hasn't been done. So for the moment, graphene is the thinnest ever material, and that's going to be the same for many years to come. Thinner than DNA. I mean, DNA, the width is around 2 nanometers, so graphene is already way thinner than that. Cell membrane is also very thin, and graphene still breaks the record, right? In terms of electronics, the smallest transistors are less than 10 nanometers. Graphene is like 1/10 of that. So if you think about like how thin is graphene, that's kind of record breaking. So it's the thinnest. Now, something that I don't fully agree is when people say that graphene is the strongest material. People say it's the strongest because it has a tensile strength of 130 gigapascals. That's a very high number. Just to check, steel is 0.5 gigapascals. Steel is very strong. So you come with graphene and you say, hey, this thing is 100 times stronger than steel. You say, whoa, this is record breaking. But how many of you will I use a monolayer of graphene to kind of do climbing? No one, right? So I know this is a very amazing number, but in practical applications, it's hard to really use graphene for like mechanical applications. So here's what I tell the students, use your criteria. this is a phenomenal number, this is a phenomenal property, but in practical terms, be careful, right? So I told my nano engineering students, if you're not nano engineering, I want you to be critical of the stuff. I don't want you just to bluff about nanotechnology. I want you to be aware of what is cool and what are the limitations. Now, the reason why graphene, or well, the people who discovered graphene got the Nobel Prize is not for any of these things about how thick it is or the strength. It is about how electrons behave in graphene. So normally carbon has 4 free electrons that can like sort of play around, but graphene has only 3 bonds, 1, 2, and 3. So there is 1 electron that is free. And those electrons do really cool stuff. They form like a free cloud of electrons above and below the carbon atoms. So this is the only question that well, just 2 equations that I'm going to show in this talk. I guess everyone who is doing like kind of sort of engineering or science remembers that the energy is equal to half of the speed squared times the mass, right? That's kinetic energy. And in physics, normally we prefer to write that energy is equal to half of the square of the momentum times divided by the mass, right? So this is a fundamental property. And we knew that electrons and electrons in gold, in silicon, in gallium arsenide, they follow this behavior. But in graphene, things are a little bit different. In graphene, the energy is linearly proportional to momentum. Instead of having P squared, it's just a linear P. So this is new for electrons, but not new in physics. In physics, there is another phenomenon that has the same equation, and that is light. Light has the same equation. Energy is equal to the speed of light times the momentum of light. For electrons in graphene, the energy of the electrons in graphene is equal to the speed of the electrons times the momentum. It is the same. And this is an equation that is characteristic for particles that do not have mass. No mass at all. I know that's weird. I still don't get it completely. I told my students, hey, you know, I didn't discover these things, but that's the way it is. These particles, light and the electrons in graphene, do not have mass. They have different speeds. The speed of light is like 1 times 10. Graphene is a little bit slower. But the fact that it doesn't have mass has huge implications. And I'm going to tell you what are those implications. When you have stuff that has mass, they interact easily. Electrons, particles, protons, neutrons just mash them against each other and they just collide, right? That's what happens all the time. But if you take 2 beams of light of different colors, you cross these beams and they don't talk to each other. They will just go straight. And they didn't know that they cross each other. That's because basically particles without mass, they hardly interact between each other. They don't see each other like phantoms, like ghosts, right? So photons do that. Gravitons also do not have mass. So that's why photons are actually good for transferring information. I can send a beam of light from here to the sun or from here to the satellite. It can go to the atmosphere. It can cross many things and the beam of light will go straight without seeing anything else, right? Electrons in graphene do the same. So basically the electrons in graphene, they do not interact with each other. And the result is the following. The speed of electrons in graphene, this is a unit of speed or less. So in silicon, it's like 1,000, for germanium 3,000, gallium arsenide 8,000. The record for the speed of electrons is around 200,000 centimeters squared per volt second. So compare this number, 200,000 versus 1,000 of silicon. Huge speed, right? That's why graphene has the potential to really revolutionize the speed at which we can process information, right? The electrons go so fast that it will just break how we think about computers, how fast 2 computers can communicate, right? And that's kind of an unprecedented capability because the electrons in graphene do not have mass. That is new physics. That's something that it's kind of hard to understand. I still don't get it completely. I tell my students, you know, if you don't get it, don't worry because I don't get it either. But just let's try to understand the math and kind of think in different ways. And that's how people start like get sense of this. So this is, I just wanted to give you 2 examples of these quantum dots, of this graphene stuff that we didn't expect, that we didn't know, but it's stuff that nanotechnology kind of enables us to do right now, okay? So, well, I just wanted to finally, Jared had this slide about just thinking for NSF because I know, most of his work he thanks for funding to NSF. NSF is great. I also have to thank NSF for, allowing me to do my research, to do outreach activities. And well, again, thanks both in the name of Jared and myself for giving us this opportunity. So thanks, Beto and Laura, and yeah.
Excellent. Thank you, Dr. or should I say Professor Vasquez Mena, because you just took us there right now, right?
I'll stop sharing my screen, right? Okay, perfect. Good.
Yeah. I don't know about many of you out there, I start seeing all these equations and I get a little apprehensive and I tighten up a little bit. So I want to thank you for bearing with us, right? And we don't want to scare you away. We want you to actually consider and think about what it could look like for you to pursue a career in nanoscience and technology. And as you saw, there's, what we see coming through is a lot of passion on many different levels by these individuals. And so next, I want to ask and lead our next question to Veronica, who's currently working within the Department of Defense and does a lot of different type of work. And Veronica, I'm wondering if you could share with us what many of those real life applications kind of look like for you, and did, as you stumbled upon, working in nano or implementing or applying nano, what did you think about it? What did it look like for you?
So thank you for that. Oscar and Jared actually are the ones that create and do the hands-on, getting their their hands dirty and getting all that stuff. I, on the DoD side, even though I'm an engineer, but I'm not a nano engineer. My piece of the puzzle for the DoD is to protect that technology from adversaries, to be able to make sure that they can fulfill their mission and continue to do their research. So in my vector, I do the cybersecurity to make sure that whatever they're using in the DoD, that we're using technologies, is protected so they can't either be stolen or used against us. What I can relate to you is there's a lot of nanotechnology that the DoD is using out in the center. And I'm going to do it on a high level, obviously, because this is being recorded and there's certain things that we can't do. But I do know that there's a lot of satellite nanotechnology that you're using. A lot of the chemistry, nanoscale structures that are embedded in there that they do. They do a lot of labs that they're trying to do research of how to build structures and different materials that can be used with our naval fleet, stuff like that. There is a couple of programs and projects that they're implementing here at NIWC that is heavily recruiting for nanotechnology engineers as well as ideas, so they can kind of put different programs together and create that nano relation to be able to support the warfighter. Ultimately, that's what our goal is out in the field. There's a lot of information and a lot of new things that are coming out, as both Oscar and Jared have alluded. That's where our future is, in that nanotechnology. And we're trying to achieve that to get there. So I know that the NSF and DARPA, which we work with as well, provides a lot of grants and a lot of dollars to do so. So what we do is we kind of grab, some of the research that Oscar and Jared might have done and re-scrub that to see what we can do, how we can fulfill that into our mission, into our new technologies to support the warfighter for that long term. But, I encourage that. Don't stop it. This is something that you are involved in, you like, keep going. You never might know, you might not be the artistic, like Oscar and Jared to create it, but you're able to help them either by providing that security element, by providing them that funding that they need, different things that they need to be able to be successful.
Excellent. So I did have a follow-up question. We have a few folks in the audience that are within computer science. And so I'm wondering, you're talking about relations with nano. Do you or any, either Jared or Oscar, would you be able to touch on any relation between nanoscience technology and coding or programming?
I mean, if you really think of nanotechnology and all the different devices that we make and the Internet of Things, right? Like, you have to have all these nano devices to be able to talk to each other. So coding's a huge aspect of that. I'm telling all of my students, in my undergraduate research group, I say the best thing you can do right now is learn how to code. Maybe start with Python and learn how to use Unity as well. Like, knowing how to do those type of abilities is going to be huge, just because there's so many nano devices and micro nano devices that there has to be a way they connect. And that's all done through coding and the Internet of Things.
Also, if you think about DNA computing, I mean, DNA is processing information, right? DNA, RNA, or transcription, or DNA takes, these molecules kind of takes decisions, right? But it's a different way of programming. So I've seen these papers about DNA computing, and I mean, the logic is different, right? I mean, it's different from the way we used to program things, like very, very kind of process flow. I think, when you think about how DNA works, that's also kind of challenging the way you think about things. So I think DNA computing and computer science, there is also a great opportunity there.
And I echo that sentiment with both of them. It's the fact of being able to have that programming knowledge in the background and be able to understand the technology to be able to say, hey, well, we can merge the two by coding, doing and testing and failing, because that's how you get to, to getting a final product. So I know that computer science is very important, and it's a pivotal capacity and skills that we're looking for in the center.
Yeah, thank you for answering that question. Computer science definitely has an important part in nanotechnology, as well as there's another question that says, where can you find chemical engineers in the field of nanotechnology? But I kind of want someone to go ahead and answer this question more as a top level, very broad approach as to kind of what are the subfields in nanotechnology and what kind of education. So what is the least level of education that you need? So for example, I didn't realize that I actually do a lot of stuff with nanotechnology. I use quantum dots in my research. But that's, life sciences. So can you please tell us a little bit about what are the subfields and what kind of education do you need for different positions, and what kind of positions can you get with nanotechnology? And that's a really broad question. So if you guys would, I'll start with Dr. Ashcroft. If you can go ahead and, lead the question. And if you, Dr. Vasquez-Mena and Veronica, if you have any input, go ahead and jump in as well.
Jared, before you answer that, I would add, is there, if I'm looking at a catalog in community college and I'm trying to pick my degree, is there something that says, oh, nanoscientist, nanotechnologist? Probably not, right? So how, what is it that I would want to put in my head that I want to major in if I wanted to go down one of those routes that Olivia's mentioning?
Yeah, no, that's a really good question. And part of our center is really trying to define what that's going to look like for technician level jobs. So, in nanotechnology, there's a lot of technician level jobs that you're probably making $65,000, $70,000 a year. Typically, they are not called programs in nanotechnology. There's only about 15 total nanotechnology programs across the country, community college. And that's something we have to work on. But you could be a clean room technician. You could work in a semiconductor nanofabrication facility where you would actually be the person in charge of etching the wafers and, creating computer chips, basically. That's all nanotechnology. And a lot of it is going remote. So, I would say a lot of things to get into is autonomous technologies and advanced manufacturing jobs. And that's if you want to go kind of a community college technician education route. I mean, there are bachelors of sciences in nanotechnology at about 6 or 8 undergraduate institutions. I think UC San Diego has one of them. So you could get a nano engineering degree from UC San Diego. There's PhD. I went to Rice University, and I had no idea nano was so big there, but that's all Rice did for their chemistry department. They were actually thinking of changing it to the Department of Nanotechnology at one point while I was there. Now, I would look at like advanced manufacturing, though, or materials science, photonics, laser technology. Even look at biotechnology. I know Olivia talked about quantum dots, which are the nanoparticles that are used a lot in biotechnology. That's really the thing that I love about nano, is that it's very widespread and multidisciplinary. That's a good thing in the sense it'll make you a very broad scientist, but a little bit of a word of warning. I had a hard time when I was applying to colleges to teach, because my PhD is kind of in nanotechnology, and they would ask me, well, are you an organic chemist? Are you a physical chemist? Are you an what kind of chemist are you? And I would say, well, I did nanotechnology. It's a little bit of everything. And that it, in some departments, that can kind of exclude you from getting that job just because they want to, are you an organic chemist or a physical chemist? So it is good. There's some benefits to having this wide range of degree in nanotechnology, but if a position is specific for one of those traditional fields, they don't understand what nano really is. So I guess that's kind of like, you can get a PhD though and work in all sorts of industries, semiconductors, biotechnology. Nano is huge right now. It's a degree that you can use in a lot of ways.
And I would add at the same time, it sounds like you can be in some of these general science, the more commonly known sciences, and there's a component of that goes into nano, correct?
Oh, for sure. Yeah. And I mean, so I see the prerequisite classes. I mean, take your chemistry, biology, and physics and try to do an introductory to engineering class, right? Like that's to me is what I would be looking for. And a lot of times what it is you're going to get your degree in a traditional field. Like I got a BS in chemistry, and then you end up going to graduate school and you'll start really specializing in something like nanotechnology, as opposed to, and I will, it's industries don't necessarily understand if we put, I have a certificate in nanotechnology, they'd even ask, well, what does that mean? And that's why a lot of times if you see advanced manufacturing or materials science, there's nano components in there, and that's what the job titles are.
I would also say it depends also what kind of nanotechnology you like. I think if you like more bio applications, then you should have like good chemical foundations. You go more into electronics, or more physics. So, mechanical properties, those are like really fundamental things that you need to have solid if you want to advance more right into nanotechnology. I mean, otherwise it's like running before walking a little bit. I remember a professor, he once kind of mocked me because I knew how to use a electron microscope, and he told me, yeah, but you cannot use an optical microscope. I was like, that's true. So yeah, I mean, you still need like your solid core of engineering, physics, chemistry, mechanical, electrical to kind of move better in nano. I don't know, Veronica, I mean, you have from your perspective of computer science.
So I know that the center is heavily on engineers and computer sciences, but it doesn't mean that, again, like Jared and Dr. Or Oscar mentioned, a variety. What happens is as you come into the center also gives you that ability to go back and get your postgraduate degree. Like in my case, they're funding me to go back and get my master's, because the more knowledge, the more skills you gather for yourself as a person, you can provide that to the center, and that's what they're looking for, is again the networking, the reach, the growth. So if you want to start off with your undergraduate degree, whatever you want, because sometimes we all end up going through a path that at the end we're like, wait a minute, I don't want to do this anymore, I want to go somewhere else, and then you vector and you love that, you can always go back and get that education. So don't let that stop you. It's just trying to make sure that you start and start with fundamentals of a bachelor's and even a master's if you're possible. Because I know sometimes it's hard to go back, but if nowadays, I remember back in the days, high school was your requirement. Nowadays, unfortunately, master is what you need to be able to start somewhere, to be able to be a lead or whatever. But if you want to do entry level, a bachelor's degree will help, as long as you go back and, finish off the ultimate, degree that you need.
Excellent. Thank you for sharing that, Veronica. And I would add, I think some of the great work that Jared has going on right now is to maybe even challenge some of those, right? And create opportunities earlier on that you can continue to build on. You can work as a systems operator while you continue to work on your degree and move up towards that master's or that doctorate degree. So definitely a lot of folks championing to do a lot of great innovative work and creating opportunities, not only that are beneficial academically, but also can provide you a livable wage, right? Which I think it's a pretty big deal when we think about it, especially if we're first generation students, we're the first person in college. It just those are very, very real life components to have to think about as we continue in our higher education. I did want to be mindful of time. We're 5 minutes over 4 o'clock. And I said 4 o'clock, but the conversations always get very scintillating here. So it's no surprise that we oozed over a little bit. I did want to do a quick recap, right? And if we talk about nano, we realize that it doesn't matter if you're in biology, if you're in chemistry, if you're in physics, you know, all of that, all of those different areas kind of lead into this nano space that is just as important as anything else, albeit doesn't have, you know, people aren't so familiar with it all the time, right? And as you heard from some of our panelists today, you know, while trying to get a job and you know, trying to open up opportunities, sometimes nano is just, it's so new and so novel to folks that's why we want to make sure that we provide this information to you as you continue to put together your plans for the future. So whether it's materials that we're studying, whether it's ways to try to make medicine, you know, higher efficacy, right, and cheaper to be able to be delivered, whether it's information systems and how we're processing that information, so many different ways that you can dive into nano and realize what a big deal it really is. I hope you see what I did there. No? Okay, I'll pretend like you all are laughing right now. But nano is a pretty big deal, and we want to make sure you walk away with that. So I did, in closing, want to continue to promote the RAIN network, also NNCI for some of you that may be educators out there, folks like SDNI, which is at UC San Diego, that also provide remotely accessible microscope, SEM. There's a lot of different tools. There's summer research programs in nanoscience, nanotechnology research that you can get involved with, both there at Pasadena City College and at San Diego SDNI, UCSD. And so make sure you take advantage of them, look them up. There's also 16 other different sites throughout the US that offer different types of summer research programs in nanoscience technology. So make sure that you check out NNCI, the RAIN network, and SDNI. With that being said, I want to thank you all once again for you know, having your afternoon with us. Veronica, Jared, and Oscar, it's been a pleasure. Olivia, thank you once again for joining us. Laura, thank you for everything that you do, and especially all those that joined us this afternoon. There's plenty of things that you could have done, but you decided to spend it with us, and we're thankful for that. Enjoy the rest of your afternoon. Thank you. If you have any questions, feel free to reach out to any of the folks that are on there. And I see that there was a question about ethics, and Jared got to answer it, copy and paste it before we close out. So you can read it and follow up with them. Thank you all so much. Enjoy the rest of your afternoons.
Thanks, Beto.
Thank you, guys.
Yeah, thanks.